In this video, we'll be focusing on how we actually store images and the sort of color spaces that are available to us. Images are composed of a series of individual pixels. So, for example, a raw 640 by 480 image consists of 640 pixels in the vertical direction and 480 pixels in the horizontal direction, which leads to a total number of pixels of 307,200 pixels, 640 times 480. Now we have a number of different ways that we can actually store these images. Now I'll show examples based on some photos from probably one of the happiest days of my life. The black and white image that we have here is the most simple of all images. Each pixel is either just black or white. There's nothing else. And so essentially in that case we only need one bit to encode each pixel. And we typically do this as a threshold. And the threshold's a common operation that we'll see later on. So if the brightness is above a certain intensity, we make it white. Otherwise, if it's below that threshold intensity, we make it black. And this is something that we often use for image segmentation problems, where we're trying to segment an image and look for key features within an image or something like that. One place we might use it to great effect is identifying fiducial markers within an image. So for our 640 by 480 raw image, we only need 307,200 bits because one bit encodes each pixel, and we have that many pixels. Our next type of image is our grayscale image. And if you compare the clarity of the two, you can see a whole lot more clearly what's actually going on here. But segmentation becomes a bit more difficult. Now, our grayscale images, each pixel has 1 byte to represent the intensity of it, or the grayness level of it, how black or white it is. And this value varies from 0, which is pure black, to 255, the highest value that we can store in an 8-bit number, which is pure white. And our black and white images that we saw previously can be very easily created by setting a threshold anywhere in this range. So we might set our threshold to 200, for example, and anything above 200 will become white, and anything below 200 will become black. So now our 640 by 480 image requires 307,200 bytes rather than bits, because we've got 1 byte encoding each pixel within our image. We then have RGB images. So in RGB 24 we have 3 bytes encoding each bit. So we have 1 byte encoding the amount of red, 1 byte encoding the amount of green, and 1 byte encoding the amount of blue. And if you open up any paint program or anything like that, there's normally options that you can specify a particular color via its RGB values, or actually look at a particular color and look at what RGB values that it actually exhibits. Here for our 640 by 480 image, we've got 921,600 bytes required to store this particular image. And one thing that we need to note is these are bitmaps. So these are where we encode every single pixel in our raw image format. Often we store them as JPEGs or something like that, which compresses them and reduces these image sizes down significantly. Another thing that can be very, very useful is changing color spaces. And so our normal color space, RGB, is fairly standard, but it's not particularly great for segmenting colors. Sometimes, and in lots of problems, we might want to search for a particular color in an image, and that becomes difficult in our RGB format. So what we can do is convert it to HSV. In this HSV color space, we store information relating to the hue, the saturation, the value of an image. The hue is essentially the base color of our particular pixel. If we look at a color wheel that we've got here, we can read off the hue as a particular angle on that color wheel from 0 to 360 degrees. So if we've got a red pixel, we'd expect it to have a hue value of approximately 0. If we've got a blue pixel, we'd expect it to have a hue value of approximately 240, give or take maybe 10 degrees. And so it can be very, very easy for us to threshold. We basically say, what's the hue value? We compare it against a couple of constraints. Is it greater than or less than this? And that can allow us to segment different colors within an image. Our saturation refers to the percentage of grey that we have in our particular pixel, and our value refers to the brightness of that particular pixel. Now, most software environments that allow us to do machine vision will have built-in functions to allow us to convert these sort of things from RGB to HSV and back and forth. In MATLAB, it's pretty easy. We say RGB to HSV. In OpenCV, we use the CTV color command, and we specify we've got an RGB image and a HSV image, and we want to use the RGB to HSV conversion. Mathematically, it's not too difficult to do. Essentially, we create R complement, G complement, and B complement, which is our RGB values divided by 255. We then calculate delta, which is essentially Cmax minus Cmin, where we're looking at the maximum RGB value and the minimum RGB value. We can then go right ahead and calculate our hue based on which of our RGB values had the maximum value. Our saturation we go ahead and calculate based if our Cmax is 0 or non-zero, and our value is essentially that Cmax value, the maximum value from our R prime, G prime, and B prime. Now, what do these actually look like? On the far left, we have our RGB value, and then next we have the hue value, and this is encoded from 0 to 360 degrees. Here you'll notice that the red flowers in particular for our hue stand out. They have a very distinctive color within this image, and so they can be easily thresholded in comparison to the rest of the image, the dress and the white flowers and the pink flowers in there. We then see the saturation, so percentage of grey, and the value, the brightness of this particular image, which looks similar to a grayscale version of the image, and is essentially a grayscale version of the image based on which color channel had the highest value associated with it, the RG or B1.